Dear students, today we will be discussing about effect of various parameter on the performance of flat plate collector and evacuated tube collector. So, there are different parameters which include design parameters, operational parameters, meteorological parameters and environmental parameters. So, while considering prominent parameters, we normally consider selective surfaces, number of covers, collector tilt, cover transmissivity, fluid inlet temperature, dust on the top cover, spacing between the covers, shadings. So, these are the prominent parameters which directly influences the performance of a flat plate collector. So, these parameters will be discussed one by one. So, now let us first discuss about selective surfaces. What is selective surfaces? The observer plate surface, what we understand now, what is observer plate. So, we consider now the observer plate surface. Okay? The observer plate surfaces which exhibit the characteristics of a high value of absorptivity for incoming solar radiation and a low value of emissivity for outgoing re-radiation are called selective surfaces. Okay? So, this surface is desirable because they maximize the absorption of solar energy and minimize the emission of radiation loss. These selective surfaces would yield higher collector efficiency than obtained when the absorptivity and emissivities are equal in case of non-selective surfaces. So, this possibility of having selective surface in flat plate collector was first introduced by Tabor, followed by Gear and Dunkel. So, what he has done? So, he used to use this spectral distribution of extraterrestrial radiation and black body radiation from a source, which is nothing but observer plate. Okay? So, if we plot it, so this peak is for the spectral distribution of extraterrestrial solar radiation. Okay? So, peak is achieved normally at around 3 micron, okay? And it diminishes at 4 micron. And if we talk about this black observer plate is something like our observer plate what we are considering. So, if we maintain that temperature of 350 Kelvin, so if we plot this radiation spectrum, so we will get something like this. So, peak will be there at around 8.3, okay? Here is the 8.3 and very less overlap has been observed here, right. So, if the surface that has high absorptivity of wavelength, so this is the wavelength, okay, high absorptivity of this wavelength of this range, okay, and low emissivity of this wavelength range. Okay. If we can make such kind of system, then we can maximize the absorption of solar radiation, right. So, what we can comment on it? So, if a surface that has a high absorptivity for wavelength less than 4 micron, so here less than 4 micron, okay. So, it is more than 4 micron and this side is less than 4 micron and low emissivity for wavelength greater than 4 micron, okay, can be prepared. It would have the characteristics desirable for an observer plate surface to act in a selective fashion, right. So, for an ideal selective surfaces, what are the desirable characteristics? This absorptivity and emissivity should be 1 for wavelength less than 4 micron and this absorptivity and emissivity is 0 for wavelength greater than 4 micron. If we can make this kind of system, then we can maximize the amount of solar radiation received in the collector system, right. So, this layer normally less than 1 micron the kind of layer what we are talking about. Say for example, this is an observer plate. So on the top of it, this layer is placed. Okay. So this thickness of the layer is normally less than 1 micron. Okay. So this is nothing but selective surfaces. So what are different methods used for making this selective surface? Maybe electroplating, chemical conversion, then anode oxidation, maybe RF magnetron sputtering, then reactive DC magnetron spattering. So there are different methods of preparing these selective surfaces. There are a host of literature. People have done research on investigation of best selective surfaces for maximization of solar radiation absorption. So it's a very good active research. So this most of the commercialized selective surface coatings are metal dielectric composite coating known as cermens. The cermens consist of fine metal particles in a dielectric or ceramic matrix or a porous oxides impregnated with metal. These thin films of these composites are transparent in the high wavelength region and strongly absorbing in the solar wavelength region, which is very, very important. Thus, they form a selective surface when deposited on a highly reflective metal surface. This coating developed include nickel black, black chrome and nickel pigmented alumina, and this is suitable for flat plate collector applications up to a temperature of 100 degrees C. Normally, for this kind of selective surfaces, absorptivity values from 0.88 to 0.94 and emissivity values from 0.28 to 0.49. So this is the range of these two parameters, absorptivity and emissivity, right. Now let us see the effect of these selective surfaces. Once we apply on the observer plate, then what happens, what benefit we are getting. So that will be demonstrated now. So this data is an experimental observations taken from a book on solar energy principles of thermal collection and storage, written by Sukhatme and Nayak. So here what is shown, two different selective surfaces and one non-selective surfaces are considered. So in case of selective surface 1, so absorptivity considered to be 0.94 and emissivity is 0.14, and selective surface 2 will have absorptivity is 0.95 and emissivity is 0.085, and for non-selective both absorptivity and emissivity are same, which is equal to 0.94. So if we see this table very precisely, what we can see, in case of non-selective surface, you can see the losses. This is the overall loss coefficient, which is about 7.26. But when we apply this selective surface, what we got is overall loss coefficient is 4.12. It's a significant reduction of losses. Okay. And here again, if we increase the selectivity or we will increase the absorptivity, so we can further reduce the losses to 3.83. Okay. And if we see the instantaneous efficiencies of all the three cases, so what we can see here, it is 43.6 for the first selective surface, which is far higher than the non-selective surfaces. Okay. And also you can see if we improve the absorptivity, we can have higher instantaneous efficiencies. Okay. So what we can conclude, by utilizing this selective surface, we can significantly improve the instantaneous efficiency of the collector. Okay. And also we can see how these losses can be reduced by applying selective surfaces over the flat plate collector. Now let us consider the case if we increase the number of glass cover on the top of the observer plate, okay, when we apply selective coating. Okay. So for example, characteristics of the selective coating is something like absorptivity is 0.94 and emissivity is 0.14. Okay? And we have considered three cases, one for single cover system, one for two cover system and one for three cover system. As we can see, this transmissivity absorptivity product for beam and diffuse radiation is decreasing with increase in number of cover system. Okay? So, here in case of single cover system it is 0.8041, then in two cover system it is 0.6892, and here you can see 0.5932 for three cover system. Okay? Similarly, there is a reduction of transmissivity absorptivity product for diffuse radiation as number of cover increases from 1 to 3. Okay? So, if we see this instantaneous efficiency which is found to be best for single cover system compared to double and triple cover system. Okay? So, what does it mean? So, single cover system is the best when we apply selective coating. So, that can reduce the maintenance cost of the flat plate collector. So, with the addition of more covers, efficiency of the collector goes on decreasing, what we have observed in the experimental table. Now, let us have a look on the non-selective surfaces. What happens here? So, let us consider the characteristics of alpha, that is absorptivity is 0.94 and emissivity is also 0.94 for the non-selective case, and also three cover system we have considered. So, in the first case single cover, in the second case two cover system, and third case it is three cover system. Okay? So, absorber plate, then glass cover 1, glass cover 2, glass cover 3. Okay? Is absorber, glass cover 1, glass cover 2, glass cover 3. Okay? So, as you can see, this transmissivity absorptivity product for beam and diffuse radiation, as the number of cover increases, so this value is decreases. Okay? And if we look into this instantaneous efficiency part, so it is observed that when two cover systems are employed, instantaneous efficiency is found to be best among these three, which is about 35.3%. Okay? So, if we increase further this number of covers, efficiency decreases, right. So, in case of non-selective surfaces, if we increase the glass cover from 1 to 2, then it is expected that we will get higher instantaneous efficiency, right. But if we increase further, so there is a decrease in instantaneous efficiency, right. So, as the number of cover increases, the value of beam and diffuse transmissivity absorptivity multiplication decreases. Thus, the flux absorbed in the absorber plate decreases. The addition of more covers also decreases the value of UL, which is nothing but overall loss coefficient. For this reason, the useful heat gain goes to a maximum value with a certain number of covers. So, that optimized number of covers need to be found out. So, from our investigation it is found that two cover system without selective surface is the good solution, okay, for getting higher conversion efficiency. Okay. Now, let us discuss something about collector tilt. Okay. So, at what angle we need to maintain for maximization of solar radiation absorption in the collector system, right. So, what does it mean if we make this kind of collector? Okay, we have to maintain some kind of beta. This is nothing but tilt. Okay. So, tilt angle. So, this tilt angle is very, very important, and this is a location specific and then time specific, right. So, these FPCs are normally used in a fixed position. No tracking is employed in case of flat plate collectors and not track the sun. Therefore, the tilt angle at which they are fixed is very important. okay, because it will be fixed throughout the year. So, when we decide what angle to be fixed for the installation, then we need to be very particular, otherwise we will be losing lot of solar radiation, right. So, optimum tilt depends on the nature of the application, right. This is also important, and there are host of literature who have developed many correlations and mathematical expression which can give the optimum value of beta or tilt angle for a particular location, right. So, Morris and Ziranki, they have used extraterrestrial radiation following a collector, and they have used this expression for calculation. Okay. This is the annual insolation which will be watt per meter square, and they are integrating with this hour angle. Okay. And then finally, the amount of solar radiation which is received in the extraterrestrial radiation can be calculated on annual basis. Okay. So, they have defined a term called relative annual insolation, okay, which is nothing but the ratio of the annual insolation for given values of phi, this is phi, and beta to the annual insolation for phi is equal to 0 and beta is equal to 0. So, once we know this, then from that also we can conclude many more things. So, let us draw what they have investigated. So, if we plot it in the vertical axis, maybe relative annual insolation, and in the horizontal axis we will have latitude, which is phi, okay, and this is valid for gamma is equal to 0, which is nothing but azimuth angle. Okay. So, if we have to make, so maybe we can use this coordinate 10, 20, then we have 30, then we have 40, okay, this is something like this, and maybe we can start with 0.7 here, then we have 0.8, then we have 0.9, and then we have 1. Okay. So, it goes something like this, then we will have this. So, this is an important observation, and it goes something like this, and then this goes something like this. Okay. So, these are the experimental points, and maybe you can point it here. So, this first line is for beta is equal to 0.9 phi, okay, and second plot is for beta is equal to 1.2 into phi, and in this case beta is equal to 1.5 into phi, and this is beta is equal to 0. Okay. So, what we can conclude here, this latitude up to 30 degree, so this is the 30 degree, small deviations of a degree or 2 from the optimum tilt will not cause much change in the relative insolation. So, this is the best one. So, beta is equal to 0.9 phi, okay, where we can get the maximum solar exposure, right. So, this plot shows the variation of relative annual insolation with respect to latitude. Okay. So, if latitude is more than 30, then you can see this relative annual insolation actually decreases. Okay. So, there are many correlations which can be used for calculation of this beta optimum for maximum solar radiation absorption in the collector. So, for winter, the recommended value of tilt is 5 plus 10 or 5 plus 15. Okay. So, phi is known, and then if we add 10, then that may be we can consider for winter months. Okay. So, what are the applications in the winter months? For water heating, space heating. Okay. So, these are the applications in the winter month if we have to use solar collector for this kind of applications. Okay. And for summer months, this tilt angle variation maybe we can keep 5 minus 10, okay, or 5 minus 15. Okay. So, in the summer applications are absorption refrigeration plant. Okay. So, once we know latitude, so from that we can calculate the beta value, right. So, now our concern is, say for some time we are trying to install a collector system to meet the demands in the winter months. Okay. So, in that particular case we need to find out the optimum beta value for maximum exposure to the solar radiation, right, for the applications like space heating. Okay. And sometimes maybe throughout the year we are interested, throughout the year we would like to maximize the amount of solar radiation received by the collector. And sometimes it might so happen that only summer months we are interested or people are interested for maximization of receipt of solar radiation. Okay. So, for all these three cases we need to find out what will be the best beta value. Okay. So, how to find out? So, this monthly average value of the energy falling on a collector plane per unit area can be calculated by using this expression, right. So, this alpha A is nothing but monthly average altitude angle at noon. Okay. So, monthly average altitude angle at noon, right. And total flux falling on the collector over the year can be calculated by using this expression. So, there are certain cases where you need to apply some other expression here. So, instead of alpha AI plus beta, sometimes we need to apply alpha AI minus beta. Okay. So, these are condition specific, right. And again, no, gamma S or gamma values, how these will vary. So, this discussion maybe we can take it up when we solve a problem. Okay. And for annual flux to be maximum, then from this expression we can differentiate it and we can find out this optimum value, which is nothing but 10 inverse of HBBI. So, this is I varies from 1 to 12. So, for 12 months we need to find out HBI value and then we need to multiply with 10 phi minus delta I. So, delta will also vary with months and finally summation of HBI we need to consider. Okay. Now, let us take a problem of something like this. The following radiations are measured for the place having phi value 8.48 north and then longitude is 76.95 degree east. Okay. So, we need to calculate maximum tilt of a flat plate collector for three different cases. Okay. In the first case, insolation falling on the area over the whole year is to be maximized. So, now I want to maximize the solar radiation received by the collector throughout the year. Okay. So, for that we need to consider all the months. Okay. And second case, insolation for the months of December, January and February is to be maximized. And third case, insolation for the month of April, May, June to be maximized. So, there are logics why these months are considered, because we have specific application during this summer and winter months. Okay. Actually, this is degree and it is minute. Okay. This is in degree and this is minute. This is degree and this is minute. Okay. So, if this is so, then what we can do? We can convert the entire phi to in degree. Okay. And these data are given. So, from January to December, HB values are given in the problem. Okay. And N values we can take the middle of the month. Okay. And we can sum it, and delta can be found out, okay, by using that equation what we have done already, 23.45 sine of 360 by 365 284 plus n. Okay. So, by using this expression you can find out the delta value for all the months. Okay. And once we know delta and phi is known to us, then phi minus delta can be calculated here, and then we can multiply this term and 10 phi minus delta, and we can see the results of this multiplication, and finally we can add these values. Okay. So, as per the expression what we got, okay. So, beta optimum for maximum absorption of solar radiation, we can use this expression. Okay. So, if we substitute these values, then what we will get is a 12.01 degree. Okay. So, this tilt angle you need to be maintained in order to maximize the solar radiation, right. And what will be the optimum tilt angle for case 2, December, January and February. So, here we need to find out these values. We need to find out December, January and February. What are those values? Okay. So, this I can explain here. So, beta opt is something like 10 inverse. So, here positive we have to apply because this part is positive. Okay. So, 10 inverse we have summation of 1.951 this term, then we will have this term plus 2.393 plus we have this term 1.833 divided by we have this and this. Okay. So, this will be something like 3.101 plus 4.162 plus 4.442. Okay. So, if we do the calculation, then this optimum value will be 12.01 degree. And for this case again we need to consider April, May and June. Okay. So, for this we need to consider these 3 values and then these 3 values. Okay. So, once you consider, and of course, you need to apply minus here because it will be minus. So, minus sign we need to apply here. So, we will get beta optimum is equal to 4.44. So, what we can conclude from this numerical exercise? So, when we are maximizing the solar radiation absorption for the entire year, then we need to keep a value of beta at about 12.01, which is the optimum value of tilt angle, which gives the maximum exposure to the solar radiation, right. And if we are targeting for only December, January and February months application, then we need to maintain a tilt angle of 16.97 degree. And for summer months, we need to maintain a tilt angle of 4.44. Okay. So, this is a very important problem, and we understand how this beta value is important for getting the maximum exposure to the solar insolation, right. Now, let us move to the spacing between the covers. Okay. So, maybe observer plate is here ABS, then we have glass cover 1, GC1, maybe GC2. Okay. So, this spacing is also very important. Okay. This spacing must be such that the values on the convective heat transfer coefficients are minimized. Okay. This is very important. The spacing at which the minimum and maximum values occur vary with the temperature difference and tilt. Okay. So, this temperature difference between this cover system and the tilt. So, this will be always installed at certain angle. So, this is beta, this is horizontal. Okay. This spacing which the minimum and maximum values occur vary with the temperature difference and tilt, which is shown here. Okay. An optimum value of spacing is difficult to specify, as the collectors are designed to operate at different locations with varying tilts and under varying service conditions. Okay. Hence, the best to use a sufficiently large spacing away from the local minimum and maximum. Okay. Let us learn what is minimum and maximum here. So, this curve was generated based on the experiments. So, it is found that when Nusselt number is 1, this conduction region with the minimum occurring at a spacing corresponding to the RL cos beta is equal to 1708. What does it mean? So, this figure shows the variation of heat transfer coefficient with spacing between the covers. Okay? And this is an example when no T mean was 70 degrees C and beta was 20 degrees C. Okay? So, what happens as this spacing increases, initially it drops to a minimum and then further increase of spacing immediately jumps to the maximum heat transfer coefficient. Okay? Then it decreases, and with increase in space finally it may come again to the below of this minimum. Okay? So, that may come something like this. So, the spacing of 4 to 8 centimeter is suggested by Buschberg et al. Okay? These are correlations which can be applied under different conditions. Okay? So, when Nusselt number is 1, so we can use this correlation which gives the minimum heat transfer coefficient. Okay? For large spacing about 5 centimeter, collector area requirements can be reduced by 2 to 8%. Okay? This is also one of the important observation, and this heat transfer coefficient H varies with temperature difference and tilt, what you can see here. Okay? So, when delta T is 10, so its variation is something like this. When delta T was 20, so its variation is something like this. Okay? So, it vary with this temperature difference and tilt, right. So, this tilt angle is very, very important for capture of more solar radiation. Okay? And also this effect of shading is very, very important during early in the morning and evening hours. Okay? So, because sun will be oblique and then one of the tubes will shade the others, okay, or the some part of the observer plate shades the some portion of the observer plate. So, that way shading also important. Okay. So, investigation of shading is really important for precise calculation of heat transfer taking place in a collector. So, shading reduces the radiation absorption by about 3%, which is estimated by many of the researchers. Okay. Now, move to the next slide. So, which shows the effect of one of the most important operating parameter called temperature. Okay. This fluid inlet temperature strongly influences the performance of a flat plate collector. As you can see here, as the fluid inlet temperature increases, this efficiency is decreases. Okay. So, this can be seen in this plot also. This plot shows the variation of efficiency with respect to the increase in fluid inlet temperature. Okay. And other values can also be seen. So, this key view is decreases, which is nothing but useful heat gain is decreases with increase in inlet fluid temperature. Okay. So, this decrease in efficiency with respect to rise in temperature is because of the higher temperature level at which the collector as a whole operates when the fluid inlet temperature increases. Okay. As a result, the top loss coefficient as well as the temperature difference with the surroundings increases. Hence, heat loss increases and useful heat gain decreases. Okay. So, temperature of the inlet fluid is very, very important as far as performance of a flat plate collector is concerned. Now, let us study about the effect of covert transmissivity on the performance of the collector, right. So, this transmissivity of the cover affects the performance of the collector significantly. So, you can realize now, because you know now how to develop the energy balance equation, there the role of transmissivity, you can realize how important this parameter is. Higher the transmissivity means lower extinction coefficient of the cover material. Also you know what is extinction coefficient. Okay? So, what extinction coefficient we need to maintain for higher transmissivity. Okay? So, as reported that efficiency of the collector increases from 43.6% to 47.4% as the extinction coefficient decreases from 19 to 4. Okay? Normally 4, 5, 6 that range is suitable for flat plate collector applications. So, as you can see here, two different selective surfaces are considered. So, one for absorptivity is equal to 0.94 and emissivity is 0.14, and in the second case absorptivity is 0.95 and emissivity is 0.085. So, if you see this transmissivity absorptivity product for beam and diffuse radiation, you can see there is a rise in those values. Okay? So, also you can see the increase in efficiency from 47.4 to 49.2%. Okay? So, by increasing the absorptivity of the selective surface, we can really increase the efficiency of the collector significantly, right. So, once we increase this, then our transmissivity absorptivity product for beam and diffuse radiation also increases. Okay. So, higher the transmissivity, better is the performance of the collector. Okay. That we understand now. So, dust which is accumulated with time on the flat plate collector as well as PV collectors are also important, okay, because this dust is nothing but it is a resistance to the flow of photons or flow of heat, right. So, when the collector is deployed in a practical system, dust gets accumulated over it, and that reduces the transmissivity of the glass cover. Okay? That is why it is recommended that glass cover or say PV system need to be cleaned time to time. Okay? Of course, it is recommended to clean daily, but it is not possible to clean daily, but cleaning is generally done in a few days. Okay? So, because of this dust which is accumulated over the glass cover in the flat plate collectors and on the PV modules, that intensity reduces. Okay? That is why we need to multiply with a correction factor. Okay? So, what is correction factor? This correction factor is the ratio of normal transmissivity to a dust laden cover to the normal transmissivity. Okay? So, in general, a correction factor of 0.92 to 0.99 is considered in Indian context, and this range is also varied for PV system or PV modules. Also, this accumulation of dust depends on the material of the cover, maybe sometimes glass or sometimes plastics are used, and tilt of the collector and frequency of the cleaning, right. Now, move to the evacuated tube collectors. So, what are objective of development of this alternative collector? To improve the efficiency, to reduce cost, to increase the operating temperature, and to reduce the weight of the collector. Okay. So, how this is done? By reducing the heat loss by convection from the top of the cover system, right? So there are many configurations. So first configurations what we can see is a flat plate type with heat pipe. So heat pipes are used. I will explain in the coming slides how does a heat pipe work. And then double walled evacuated tubes. Okay. So evacuation is maintained, this vacuum is maintained between the tubes, so that convective heat losses can be minimized. And the third configuration is the water in the glass type. Okay. Here some kind of reflectors are used to heat the fluid. Okay. And finally this is collected in the storage tank. Okay. Let us learn in deeper sense these evacuated tube collectors. This evacuated tube collector consists of a number of rows of parallel transparent glass tubes connected to a header. So these are the headers and these are the tubes through which heat transfer fluid flows. Okay. These glass tubes are cylindrical in shapes, okay, as you can see here. Therefore, the angle of the sunlight is always perpendicular to the heat absorbing tubes, which enables these collectors to perform well even when the sunlight is low. Okay. So this is very important point. Even though sunlight is low, this evacuated tube collector will work perfectly. These evacuated tube collectors are particularly useful in the areas with cold and cloudy weathers. Okay. So that we should keep in mind. This tube diameter normally keeps in the range of 25 to 75 mm, okay, and length is about 1500 to 2400 mm. Okay. So this each tube consists of a thick glass outer tube and a thinner glass inner tube, which is covered with a special coating that absorbs solar energy but inhibits heat losses. Okay. So selective coatings are applied so that energy absorption can be maximized. The tubes are made of borosilicates or soda lime glass, which is strong, resistant to high temperatures and has a high transmittance for solar irradiation. These parameters are very important as far as evacuated tube collectors are concerned. So what is the difference between this collector and conventional flat plate collector? These evacuated tube collectors do not heat the water directly within the tubes. Instead, air is removed or evacuated from the space between the two tubes, forming a vacuum. Okay. This vacuum acts as insulator, reducing any heat loss to the surrounding atmosphere. Okay. So these are the tubes. Okay. So here this is the vacuum, and since no medium is there, so once heat is introduced, that heat cannot be come out. Okay. So it's a insulation. With the assistance of this vacuum, the evacuated tube collectors generally produce higher fluid temperature, okay, which is more than flat plate collector. Sometimes we can get a temperature more than 130 degrees Celsius. So it is seen that heat pipe technologies are used in evacuated tube collectors. What is heat pipes? Heat pipes is nothing but an heat exchanger, which combines the principles of both thermal conductivity and phase transition to effectively transfer heat between two solid surfaces. So what happens if we consider this configuration? So fluid is here in this tube. When solar radiation is exposed here, then this fluid will be evaporated, okay, and then this latent heat of evaporation will be released here in the condenser part. This is a condenser part where heat will be carried, okay, and then once it is condensed, it will flow in the tube under the action of gravity or capillary. Okay. So this will maintain and this will be circulated again and again. So heat will be carried by this fluid and which is deposited here where heat is collected, and then it is condensed and this come back to the original position and it moves in between the closed circuit. Okay, and this is vacuum. Okay, this vacuum is maintained so that energy losses are minimized, and this is the glass tube. Okay, and liquid return is shown here, and fluid is something like alcohol like fluids. Okay, and this is called vaporizers, and this is as a whole called heat pipe. Okay, this part is heat pipe. Okay, this part is heat pipe, right. So in heat pipe evacuated tube collectors, a sealed heat pipe usually made of copper to increase the collector efficiency in cold temperatures is attached to the heat absorbing reflector plate within the vacuum sealed tube. Okay. The main advantage of this heat pipe evacuated tube collector is that there is a dry connection between the absorber plate and the manifold. Okay. So there is no wet connection, no fluid will be contacted. So this is a dry connection. Okay. So this is a very good technology and efficiency is very high, but somewhat costly. And also direct flow evacuated tube collectors are in place. Okay. So here two heat pipes running through the center of the tubes are used. So as you can see here, solar radiation falls here. So it is a cold fluid in and the hot fluid out is here, and then evacuation is maintained, and it's a U tube. Okay. And of course this energy absorption can be maximized by using these kinds of plane reflectors. Okay. So one more advantage is that this direct flow evacuated tubes can collect both direct and diffuse radiation and do not require solar tracking. Okay. So principle of working is same as heat pipe collectors. There are other collectors like BNL collector, then polymer solar collectors and concrete collectors. Okay. So we will not discuss more on it. So these are the available collectors, and most of the collectors in under research condition. So we can summarize what we have discussed today. Primarily we have discussed different factors which influences the performance of a flat plate collector. Primarily we have discussed selective surfaces, how selective surfaces can be manufactured, what are the importance of selective surfaces, okay, and what are the range of absorptivity and emissivities for selective surfaces, okay, how we can enhance the absorption capability by increasing the absorptivity of the absorber surfaces. Also we have seen the effect of number of covers with selective surfaces and without selective surfaces. Also we have studied the influence of spacing between the covers. Also we have studied the role of collector tilt and dust on the top cover. Finally, we have understand how this evacuated tube collector works and what are the need of development of this kind of technology, of course for increasing the conversion efficiency by reducing the cost. Okay. I hope you have enjoyed this lecture. Thank you very much for watching.